Thanks, Ravya. And we'll have our next presenter. The next presentation is by Dr. David Weiner, and the presentation is on plan design goal recognition with autoencoding transformer for the Cerbrec modeling platform. David Weiner, the platform is yours. I can see your screen, but cannot hear you.
Yeah, I had to try to unmute myself. Okay, great. So, yep, we're just talking about plan design goal recognition with auto-encoding transformer for the Cervic modeling platform. And everybody can see the screen, I guess, she said. So first I'll describe the general form of the goal recognition problem, and then I'll get into how it applies to our motivating task. I'll talk about how we try to learn this task. So rather than acting directly in an environment, imagine an agent is designing a plan on a whiteboard. Can you guys see my mouse, by the way? Is that a no?
Yes.
Yeah, you can see my, oh, thanks, Garrett. So here we have an environment and there's the steering agent, and the steering agent's not acting directly in the environment, but it's acting on the plan design to create its route. So the plan design actions are actions like remove a right turn and add move forward. And along the way, it's actually creating plans that aren't executable, by accident, right? And sometimes they're undoing their previous actions. So what this agent is doing is something like plan space planning, where each step by the agent is an edit to the plan, and the agent is behaving on a path towards creating a final plan design. That's the agent's goal. So the recognition problem is to determine what the final plan is, what it is that the agent intends to design. And that's the goal state for the agent on a plan space path. So if the observer can successfully recognize what the agent is trying to achieve, then it could help give recommendations about what edit to make next to the plan. So Cerbric is a platform for designing machine learning models as plan-like artifacts. So rather than path planning on a whiteboard, here we're looking at Cerbric as this base domain where users are in effect plan space planning out the flow of data across a network of operations. So a little bit about the functionality of Cerbric. Users can select schemata from the left side here and drag them into the graph. Then you could copy and paste and do your visual editing. If there's time at the end, I will do a live demo of Cerbric. So with Cerbric, you can see the shape and the type of your data at every variable. And so each operation here is takes data as input in the form of slots and produces new data. And so these links are bindings from the output of one operation to the input of another, meaning they have to share the same data. And so here we're looking at an example, which is a natural language tokenizer. You can see that it's actually arranged hierarchically. And you can see some operations actually have this little expand icon. That means that they decompose further. And in Cerbric, it's useful to organize your content around being hierarchical, not just for organization, but because each operation can actually be served outside of the application with specific computing resources via an API. So the inputs of the operation are actually what are exposed, the exposed inputs of the model outside of the application. And so all operations are fully decomposable into primitive operations like add and multiply. And you can see how data flows through every part of your model. And there's no black box. And again, I'll give you a demo later if we have time. So full disclosure that Garrett and I, the paper's authors, are the co-founders of Cerbric, which we're on a mission to make Cerbric, to make AI development easier to understand and more productive. and I'll end with some additional information about that. And so basically, the user would log in and there's some pre-built components, or they can start from primitives from scratch, and then everything's available on the cloud. So Cerbric operations there are instantiated from schemata. They have a similar purpose to strips operators, but there's some notable differences. We use the term operation schema to refer to the template, and then we use the operation to refer to an instance of that template in a plan. And so each operation has inputs and outputs, and you can see they have a place to be assigned data. And then there are some constraints. These characterize the shape and type of the data that can inhabit them for that operation to execute. If this was a composite operation schema, then it would also have a place for a subplan. And so the constraints are compiled in a graph, and we run this propagation method so that the influence of each constraint travels as far as it should. So in this example here, even though there's no data supplied to this transpose operation, we know via constraints from this right operand of add that if right operand has to match the shape and type of the left operand, and this binding means they're equals, and then via the constraints of the transpose operation, we know that it has to have shape 2, it has to be 2 by 3 and a decimal, since the right operand was 3 by 2. So one of the benefits of Cerbric is that it's easy to see if you're creating an error. So there's been a lot of recent research about the most common issues that developers have with deep learning frameworks. And the number one issue is errors related to mismatch of data shape and type. So there's a lot of reasons that users might violate constraints and not realize it. So maybe they need to tile or scale a data point to a specific shape, or they don't check that what data type is expected, because typically there isn't this visual element which Cerbric provides. So with Cerbric, if the user tries to supply data from one operation to the next, but the constraints are violated, then the user sees this error and the consuming operation doesn't execute. And so if I were to right click, ignore. Okay. So if I were to right click on this error here, then it would give me some suggestions about how to fix this error. And so that's really where the motivation of this paper is. So we want to recommend an edit to the user's plan that incorporates their goals based on their design so far. So maybe they're doing data preprocessing, maybe they're designing some metrics for their results. Whatever it is, we want our recommendation edits to be context sensitive. So the motivating task here is we want to recommend context sensitive edits that bring a user's current plan to a likely goal state. So in this paper, we describe an approach to learn the context and next best edits in a way that can generalize to unseen plans. And to do that, we take inspiration from language modeling. So our strategy is to encode Cerbric plans as vectors by adapting the BERT architecture. So with BERT, typically you have a vocab map. So after you tokenize your sentence, you have a map, you map each of your words or subwords to a specific vocab ID. So with our adaptation, we actually have a binding map, and we have a specific binding ID for every possible binding link between schemata. So then the plan is fed into BERT as just a list of binding IDs. And then we do something called masked binding modeling, which is like masked language modeling. So we mask one or more binding IDs and try to recover them. So that's our pre-training process. And we're currently only doing that with pre-built models that are fully complete. So the embeddings are based on recovering complete models. And we also describe in the paper a novel adaptation to encode the relative positionality of the binding IDs. So instead of linear positionality like language, we want to actually use the partial ordering of the plan to interpolate weights. So we use Cerbric to design our solution. So to clarify here, we're using Cerbric as both the case study for our applied task, as well as the implementation for our solution. And so this is part of the implementation of BERT, where we show how we add the positional weights after we do the scaled dot product. And this is in the self-attention part of the layer. And you can see that the shape and type of the data at each part. And so the dream really is that maybe that scientists can actually show a functional diagram of their solution like this, instead of just a visual representation of an architecture, but we're still getting there. So for this, we do a fine-tuning step where essentially we reverse plan a goal model into a perturbed plan by taking one or more perturbation steps. So essentially we randomly mess up a goal plan, meaning a complete plan, a complete model that we've offered as a pre-built component. And so the resulting plans are these unfinished, meaning they have some kind of unfulfilled variable, right? So they don't have a binding link to some of their inputs, and they can also be invalid, meaning there's some violated constraint. So now I'm going to kind of walk through this fine-tuning, how this fine-tuning task works. So here the input is these pairs of goal perturbed plan pairs. And then, so we pretend that that perturbed plan is like the user's current plan. And then we do this process where we then expand that plan into, via the edit space. So every possible edit the user could make is then all of the children plans. Oops. And so one of those children plans is actually the correct plan, meaning it's on some, it's actually on some path to the goal that doesn't get undone. And we figure that out using the planner. So then the parent plan and the children plans are, they're all encoded via this binding embedding layer that we pre-trained with masked binding modeling. So now we have an encoded parent and these encoded children, and those are all vectors. And then the parent vector and the child vectors are compared through these plan space distance weights. So this is really a second layer in the neural network. And so the predicted child is compared to the actual correct child that we got from the children plans. And so then we are back propagating that contrast through both layers. So in essence, we have this 2-layer neural network, and where the task is to select an edit, and the distance between the encoded plans and the parent corresponds to that next best edit action. So, and here's the actual model architecture for the prediction generation. So we have the parent and we have all of the children. We encode these into the plan encoder. Then we average the binding embeddings to create the plan embeddings. We multiply those by the plan space distance weights. So you can see those distance weights have the hidden layer size times our new hidden layer, a second layer size. And then we pick the child plan that is most similar to the parent plan. And this is not for the learning stage. This is for the serving of a prediction. So we don't have any results ready. We're working on validating the fine-tuning approach. And we want to test different perturbation policies, because random isn't always good. And it's sometimes leading us to unfinished plans, or sometimes it's getting us closer to other goal plans. And so there's some parameters that are still being worked out. And we also really want to validate on actual user interaction traces, since Cerbric isn't actually available yet. And so we want to make sure that when we collect interaction traces from beta testers, and then we'll start seeing if that data can be used for our fine-tuning process. And finally, we want to see if users like the recommendations that we give them. So we'll compare the policy for giving those recommendations to some maybe more naive baselines. And so in conclusion, we talked about plan design goal recognition. I introduced the Cerbric modeling platform in a shameless plug. We talked about the novel auto-encoding adaptation and our fine-tuning task to learn action selection. And so Cerbric is going to be a free-to-use platform where you'll only pay for cloud fees related to training and serving, and then otherwise just running the model over sample data is going to be free. And so, yeah, let me know if you'd like a private demo. We're actively finishing up development for a public release for beta testers. And we're looking for scientific advisors and collaborations, beta testers and investors. So I think this would be a good place to see if anyone's interested in getting involved. So I'll leave it open to questions, and then if we have time still, I'll do a quick 2-minute demo.
Sure. Thanks, Dr. David Weiner. And yeah, I have a quick question. So what does the plan encoder do in your specific model that you've been showing? What does it actually do?
What does the plan actually do? Yeah, so
Plan encoder.
The plan encoder.
Right.
So what the plan encoder does is actually just follows the same thing as like the BERT architecture, right? So in essence, via the masked binding modeling, where we're trying to recover, so we make a prediction via these, the BERT architecture. I don't know if I'll want to get into that, but essentially you can just think of it, it's just BERT with some notable differences, and they're detailed out in the paper. Does that answer your question?
Yeah, it does. Thank you. And yeah, you can show the demo. You still have 2 minutes left.
Yeah, sure. Let's do it. So let me change where I'm presenting. I can't find any of my windows, of course. Where's everything? Let's quit this. How do I get out of here? Show all windows. Nope, not working. Okay, I'm struggling to find where my things are. Well, that's why I don't do this in the beginning, right? So, where is Zoom? It's not showing up for me. Oh, there it is. I got it. Sorry about that. Okay, let's do desktop, share desktop. So I'm just logging in now. Cool. So I'll just quickly, I'll show that, okay, so you can drag and drop like an add operation here, and I'll put in some quick, you can bootstrap values if they're small. And so then they just get, instead of being fulfilled by a binding link, they appear as circles, and you can see the results below. Then if I copy and paste this thing, I can take the output of one operation and feed it to another. So now you can see that it went 5 plus 3, and then I can actually replace this value, and you can see the final result is updated. If I try to feed this thing some text, so here we know that the output has to be text. This is expecting a decimal. Then if I feed this into here, it's going to produce an error on the hover over. And finally, the other thing I'll just show real quick is that if we, let's put in some sample text here, like this will test the tokenizer. Okay, so that's some messy text here. And if I feed that through, you can see, okay, it's split it up into some words here based on some regular expressions. And if you want to, the cool thing is that this expand button means that I can actually dive in, right? And I can see how it goes from the input bar here. This is like our dummy operation. You can see every step of how the data was constructed. And you can even remove operations. You can see it stops flowing. And then if I put it back in, it recalculates everything. So that's kind of the basic gist of it to show the decompositionality.
Sure. Thanks, Dr. David Weiner. And
I have a quick question, or I don't know if we have time.
Yeah, sure.
So can you set it up in such a way that if you have, like, you can, so I'm imagining it would be nice if you can basically put the data you're starting with, and then you have some desired output, obviously. And then as you play with it, you could see what the final result is. Is that something you can do with it? So then you can see kind of if you're getting close or if you're making progress for the end state, basically.
So for the end states, let's say you have some output operations and you basically are saying, I want to get this close to some goal vector or some data that I know it should look like. Currently, what you could do is you could just kind of keep playing around until it create, and look at the data side by side. There's no way to take output data and backtrack your way to how did I compute that, and that's sort of the goal here, right? Is but what we're doing is more on the plan structure. But yeah, you could in essence imagine that would be something we would want to make happen, but yeah, we don't have that yet.
And also, thanks. And just a quick follow on. Do you think people, when they start out using this, they would start out from like a desired end state and work backwards? Or do you think it'd be mostly people who kind of build it up from the beginning because they have some way of knowing what operations they're going to use?
I think that people will start with some data that they are bringing themselves, such as like at a company, we have our data, let's get it. And then they'll drop in a pre-built like BERT model, and they'll feed in the inputs. And then if they want to make changes, they can actually see live how that's affecting every part of the model. So that's how we envision people starting. So you would start with your own data, and you wouldn't work backwards, because I think in general, in most model prediction cases, you would have some like training data that you'd be using.
Gotcha. Thanks.
No problem.
And Dr. David Weiner, we have another question from Dr. David Eha, and it's thanks for your interesting presentation. Is Cerbrec focused on intelligent agent development, or is it just an example of what it can do? And it's more generally designed for any type of software development?
Yeah, so we're focusing on making AI model development easier, and we're starting with natural language processing as sort of our main focus for who the users are. So these are data scientists. Maybe they're actually they don't have computer science degrees, or they do, but they want to be able to design models easier. And so we're converting, some TensorFlow or PyTorch models into Cerbric models so that they're available for users. Now, in this paper is introducing a way to learn from users' interaction traces so that we can actually kind of give you suggestions on the fly, do intelligent code completion. And so this is something that's in active development, and where we would have, basically an assistant in the platform, helping users, especially when they come across errors. How do they fix those errors? I think that's answered. Let me know.
Sure. And yep, I have another question from Erickson. How radical is the jump from sequential input token ordering, as in a conventional language model, to precondition constraints?
How conventional was, can you repeat that?
How radical is the jump from basically sequential input token ordering in conventional language model to precondition constraints?
What do you mean by precondition constraints?
The plan.
Like the constraints in the operation?
Yeah.
So those constraints are basically not, sorry, I was reading the questions. So those constraints are not encoded into the model, into the plan, like the Burr architecture. Those are just to calculate whether your plan is valid or invalid and where the errors are. But the encoding of the plan into the vector is absent to whatever changes we make to the constraints. So, as part of development, we're trying to knowledge engineer these primitive operations and the constraints around their data shape and type. So yeah, that's what I have to say, I think, about that.
Sure. Thanks, Dr. David.
I've never been called doctor so much.
Sure. Thank you, everyone. So we have finished our session 1, and we'll be heading to session 2 after the lunch. So we'll be meeting at 1:30. And during this time, we would encourage any discussions in this Zoom channel or Slack. You could visit the others, specific other papers channel, and then perform discussions around that. And I will send you a heads up message in Slack channel as well as on Zoom before we start our next session. And thank you very much, guys. And if you have any questions or any comments, please feel free to reach out, either me or Stravia or Zora. We can get that figured out. Thank you, everyone.